Good evening and a very warm welcome to the fibUK June lecture. My name is Corin Walford and it is my pleasure to be chairing this evening's event. Our topic this evening is tall concrete buildings. Tall buildings have become a prominent feature of modern cities. As our society strives to solve the issue of creating places to live and to work for our increasing populations, this has resulted in a drive for ever increasing height in our tallest buildings. It presents today's structural engineers and builders with a set of new and unique challenges to solve, which ultimately has led to the creation of some of the most iconic buildings of the modern age. This evening, we have three expert speakers lined up, covering state-of-the-art research and two fascinating case studies which delve into some of the challenges faced in tall building construction. Now, I'm delighted to introduce our three speakers for this evening. First to speak, we have Jia-Yu Long, and he is currently a PhD student at Imperial College London, where he is also a teaching assistant covering structural mechanics and computational methods. His research focuses on the design of transfer slabs for shear, and this evening he'll be sharing some of the findings of his research. Secondly, we have Christian Tagore. Christian is a technical director at AKT with over 20 years of experience in structural engineering. A graduate of the Technical University of Berlin, he brings deep expertise in concrete design, finite element analysis, and automation to drive innovation and efficiency in structural engineering. His presentation this evening will focus on London's Bankside Yards West development, including the very impressive 53-story Opus residential tower. And finally, this evening, we have Pavel Gruber. Pavel is a practicing structural engineer and a project director also at AKT with 15 years experience in the design and management of large, complex, mixed-use developments across London. With a master's degree from Wrocław University of Technology, he has built a strong technical foundation that underpins his innovative approach to solving technical challenges. Pavel will be speaking to us this evening about the Nine Elms development in London with its pair of equally impressive skyscrapers, the taller of which soars to a dizzying 208 meters above the nearby River Thames. So without further ado, I will hand over to Jia-Yu Long, who will take us through some of his research.
Hi, thanks, Cory. Hi, everyone. I'm Jia-Yu Long, a PhD student from Imperial College London, supervised by Professor Robert Volume and Professor Lorenzo Maccarini. My research is about the influence of planted column offset on shear resistance. In today's talk, I will discuss the design of transfer slabs for shear. So this is the outline of today's presentation. Firstly, I will briefly introduce the background information of shear failure in transfer slab structures. Then I will show the calibration of material parameters in NLFEA software Athena. After that, I will demonstrate my recent research, which is about simulating a typical transfer slab structure in Athena and GSA. Then I will make comparisons between those simulated results at both linear shear and punching shear check in the next generation of Eurocode 2. In the end, I will give design recommendations based on transfer slabs I simulated and give comments about the shear checks in the next generation of Eurocode 2. So what is transfer slabs? This is a type of structural members often used in multi-story buildings where upper floors and lower floors are of different usages. Each of these floors may require different column arrangement to optimize the space, leading to a deviated column layout. The right figure shows the typical concentration of shear force in a transfer slab. As you can see, it's very complicated, and this complex shear force distribution can lead to different possible failure modes. So what are the possible failure modes? The question can be answered by a related problem of cantilever bridge deck. The left figure shows previous tests reported by Cantoni. Those cantilever bridge decks were supported by a line beam and subjected to either a concentrated load or a line load, as left figure shows. Test results show that different load arrangement can cause different failure modes. During the test, the one subject to concentrated load was eventually failed by punching shear. You can see a clear punching cone is formed around the loading plate, whereas the one subject to line load was eventually failed by linear shear. The cracks are much wider and straight, so both punching shear failure and linear shear failures are possible failure modes. Then moving back to transfer slabs, the only research on this type of structure is by Wang and Volume. who looked at transfer slabs with closely offset columns. Their research found out that within two effective depths, so within 2D, the shear resistance is increased by the direct strutting actions, and the diagonal cracks are reduced. As a result, the concrete resistance is increased by this triaxial compression, but what happens when shear span is greater than 2D remains unknown. To investigate this problem, I use NLFEA software Athena to determine the failure mechanism. The modeling parameters on reinforced concrete were adopted by Wang, which was validated on previous punching tests, as well as the tests of Wang and volume, in which specimens were loaded under combined upper plate loading and perimeter loading, as figure on the left shows, and detailed material parameters are listed in the right figure. So we're using rotating crack model for concrete with compressive displacement of 0.2 millimeter and compressive strength reduction of half of concrete strength. Then we also simulated punching tests of lips. The left figure shows the mesh arrangement we adopted for the simulation. The sensitivity study of different material parameters are plotted as figure on the right. So results show a good match between Athena results using Wang's parameter and test result. Then after that, we started to look at a typical transfer slab structure. The geometry of the structure is as figure shows. The two major loading we consider are the upper column load, which is the load induced from the planted column, and UDL load, the uniformly distributed load acting on the slab. Then next slide shows the plan view of the transfer slab. To save computational time, only a part of the floor is modeled. We call two subassemblies, the large subassembly and small subassembly. The line A in the figure is the symmetry line. The blue and yellow lines are the boundary of a small subassembly. The size of the small subassembly was adopted by a similar size subassembly of 1, in which the width of the specimen was taken as approximately 0.44 of the span, corresponding to the radius of contraflexure on the UDL load in the east-west direction. The length was taken so that the boundary shear was on two halves of long side, as the blue lines in the figure is equal in magnitude and opposite in direction. Note that this is a very typical size of punching tests used in the laboratory. Subsequently, we increase the size of the subassembly, as red rectangle shows. The purpose of large subassembly is to investigate the influence of subassembly size on different load combinations. The large subassembly has 4 bayways, and the length is taken from the symmetry line to the edge. So in total, 6 meters times 9.2 meters. Then next slide shows the dimension of two subassemblies. The material parameters are listed on the left. The effective depth is taken as 400 millimeter. Reinforcement ratio in top and bottom. Longitudinal and transverse directions are all 20 at 150 millimeter spacing. This is a typical reinforcement ratio used in practice. The lower column is kept at the same distance, and relative location of the upper column changes so that the shear span varies from 2D, 3D to 4D. Apart from ultimate failure load, it is also important to know the failure mode of the structure. So what is the failure mode? Is it a punching failure or a linear shear failure? Does the failure happen around upper column or lower column? One way of distinguishing it is to examine the critical cracks at the ultimate failure step, but sometimes it can be very hard to tell the difference between cracks of linear shear failure or punching shear failure. For example, as two figures on the left show, the cracks around upper column resemble, but top figure is filled by punching shear, whereas the bottom figure is filled by linear shear. So we did extra things to distinguishing the failure mechanism. We found out that for the test in the laboratory, the critical shear cracks are associated with thickness change. A new way to monitor the vertical expansion in Athena is developed. If there is a thickness change around 0.5D away from the column, then it is likely to be filled by punching. If thickness changes around 1D, then it's more likely to be filled by linear shear failure. Then moving to the next slide is the interaction diagram of my Athena results from 2D to 4D gap. The x-axis is the total UDL load on the slab, whereas the y-axis is the upper column loading. The green dots are slabs that are filled by punching, and red rectangles are slabs filled by linear shear. On the pure UDL load, so when the y-axis equals to 0, all subassemblies are filled by punching around lower columns, and failure loads are similar for small and large subassemblies. But interesting things happen when upper column load increases. The ultimate failure load of small subassemblies drop much quicker than large subassembly. The small subassembly begin to be filled by linear shear, whereas large subassemblies are still experiencing punching failure. We believe that the reduction of ultimate failure load on the upper column loading is associated with the shift of failure modes. But what's the reason of shifting failure modes? To investigate this phenomenon, we look at the worst cases, which is the shear span of 4D on the pure upper column loading. The left table shows the intermediate size of subassembly I have looked at. It is found out that the failure mechanism is largely influenced by the width of the subassembly. As the width of the subassembly decreases, the failure load decreases and the failure mode shift from punching shear to linear shear. Besides, the failure location changes from both columns to just around upper column as length of the subassembly decreases. Furthermore, the evolution of shear force over width of the subassembly is compared for each D along the gap. The shear force in the diagrams are normalized so that the lower column axial load equals to 1 kilonewton. It is found out that the shear redistribution occurs over the 6 meter and 4-meter width subassembly in the midway between two columns, but not over the 2.7 meter wide subassembly. This suggests that 2.7 meter subassembly does not capture the shear redistribution behavior well. Besides, we also calculate the shear resistance using the next generation of Eurocode 2 with LFEA software GSA. The formulas on the left are the shear checks we use for calculation. The punching shear check is made at 0.5D around both columns, whereas the linear shear check is made at 1D away from both columns and midway in between over a width of 4D. When calculating punching shear resistance, there's a factor beta E, which accounts for the concentration of shear force, and it is calculated based on the shear field analysis. As the right formula shows, the V per ab in the equation is the average perpendicular shear force. In the calculation, the critical length can be chosen to be either a quarter of the parameter or a half of the parameter, denoted as punching half and punching quarter. Then the perpendicular shear force at different control sections are compared for small and large subassemblies in Athena and GSA. Again, the shear force is normalized so that the lower column axial load equals to 1 kilonewton. The shear force shows good match between large and small subassemblies. The right side figure are the interaction diagrams for comparison between Athena and codes. As we previously mentioned, there is a huge difference in ultimate failure load for large and small subassemblies on the upper column loading. Although the shear checks in the next generation of Eurocode 2 are actually similar for both large and small subassemblies, different conclusions are drawn for two subassemblies. For small subassembly, the linear shear check gives reasonable predictions for pure upper column loading, but very conservative on the pure UDL. For large subassembly, punching check quarter gives good results. Here are the conclusions for everything. On the upper column loading, the ultimate failure load reduces as shear span AV increases. For UDL load, the failure load is independent of the shear span. Then modeling large subassembly of 4-bay width instead of at the radius of control fracture is needed to correctly capture the shear redistribution behavior. Then the next two conclusions are about the next generation of Eurocode 2. The linear shear check over width of 4D is considered conservative. The actual failure load is increased by the shear redistribution behavior. Then the punching shear check over the core control parameters show good prediction. That's the end of my presentation. I will pass on to Christine Taglo.
Good, thank you, Joe. My name is Christian Tiger. I'm Tech Director at AKT2. Today I'm going to present the Opus building of the Bankside Yards West project. Just a brief introduction to AKT. We are kind of a structural engineering practice based in London, but we also have sort of offices in the UK regions and overseas. Our headquarters is in London, and sort of most of our projects are thus in London as well. With respect to sort of tall buildings, sort of it stretches from sort of in the west, from the Nine Elms area, with one Elms project, which my colleague Pablo will talk about, to the east in Canary Wharf, the kind of Wood Wharf projects over there. Coming back to sort of the projects I'm going to present, it's a scheme developed by Native Land with two architects on the site, PLP and Make. And the project has been delivered by Multiplex Cementation as a piling contractor, McGee's for basement construction, and Calbray for the delivery of the Opus building. The site itself is located in sort of the South Bank, just sort of next to Blackfriars, sort of sandwiched between sort of Blackfriars Bridge and sort of viaduct of the Blackfriars station. On the site, there are sort of the western part of the master plan. To the west of the Network Rail viaduct are sort of three buildings. They're called sort of Building 3, which is a steel tower with 20 stories. Building 2, which is the Opus building, residential tower, and Building 1, which doesn't quite know what it wants to be at the moment. I think it's planning for like an office scheme. The sort of ambition of sort of our client Native Land is sort of to deliver a high-end sort of residential scheme with sort of what you would expect for this amenity spaces, sort of winter gardens, car parking, and so on, and also to sort of establish in the later stages a connection from the east to the west underneath the Network Rail sort of viaducts. The sort of project is to sort of be delivered in a phase of development and phase construction, starting from the south to the north. Building 3, the Arbor building, is sort of complete since almost 2 years and is occupied. The Opus building is currently under construction, with the structure being almost complete or near completion. As you can imagine, this is like an inner city development with sort of many constraints. Just sort of to name a few, we have a Network Rail. You've got a BT tunnel crossing the site, which we are technically not allowed to talk about. Sort of UKPN sort of cables crossing the site, which we sort of had to divert. There's a river, all of the sort of interfaces to the environmental agency, tunnel sort of like to the south, kind of trees, and the sort of existing foundation remnants of the existing or previous development. In terms of ground condition, is kind of what you would expect sort of like from sort of an inner city London development, with sort of alluvium, terrace gravels, clays, Lemeth Group, and chalks. And we have a relatively high water table because of proximity to a river, and therefore have sort of like a close off basement, which I'll sort of show on the sort of next slide. In terms of basement structure, so bear with me. This is like a tall building one, so to say just a few words. The basements of in this And the substructure sort of consists on a sort of secant wall, which basically is all around the perimeter of the site. The sort of foundation system consists on a piled raft, which supports the building on large diameter piles. We have a sort of a level 2 basement, sort of typically, with a deeper section for a level 4 basement housing a car stacker, and the whole basement is sort of formed in reinforced concrete construction. The sort of basement, which is largely complete, has been developed in a mixture of bottom-up and top-down construction, with top-down being on sort of plunge columns, to facilitate sort of servicing the site and sort of in terms of loading areas and the likes, and to get sort of muck and other things out of the site, and sort of cross-propping sort of coordinated with the sort of permanent structure. As you can imagine, we had sort of been quite busy with all the sort of approvals, and sort of the asset owners who are the technical team spent sort of months on kind of refining the analysis and of the foundation design, and also going through the approvals with Network Rail, so UKPN and the other asset owners. Coming back to the sort of superstructure, so we have, as you can see on the sort of elevation of the buildings, we've got sort of like 49 floors now, with a change in massing at level 21 and 39, so we have setbacks. The sort of apartment layouts of change across the floors, and the mixture of the apartment changes, which sort of requires sort of a careful coordination of the column locations. Sort of clients sort of my obvious request is to minimize the column sizes to basically maximize the values. We have a sort of a 250 PT slab for the structure, and the core walls, just to give you highlights, range from 400 to 300 mil throughout the building. We looked at sort of at the early stages. I forgot to mention, we started the design of the projects at stage 2, at concept stage, in 2015. It's kind of through various options for columns. We kind of in the end sort of settled for a mixture of reinforced concrete columns of various strengths and composite columns. That was sort of mainly to carry the forces and keep the slumming to the columns small in footprint, and also to control actual and differential shortening with the use of these columns. The sort of core layouts and sort of stability system sort of evolved and kind of responded, as you can see on the diagrams, during sort of stage 2. So it's like probably barely see from a sort of squarish compact core with sort of shear walls, to a sort of slightly sort of elongated core, still requiring shear walls in east-west direction. And we kind of used sort of like a catalog of sort of studies or techniques, like during that process and the design, sort of to explain to the architects the sort of effectiveness of sort of spandrels, kind of changes in wall thickness and use of outriggers, and sort of carried out sort of a comparison of sort of various option and combination of these options, probably in total around 30-ish options we looked at, just to sort of like develop their understanding which elements of a stability system are important and which ones we can change or easily modify with sort of an ever-changing core layout. So we kind of then settled on in terms of the design or stability system, on a system of core vaults around sort of the services and staircases and lifts, spandrel beams and spine vaults. And this sort of illustrates the sort of core layout where we arrived at the end of stage 3. The sort of governing criteria at sort of that time was the building accelerations, not necessarily deflections and story drift, and we assessed that using the Canadian codes. Since we sort of EU codes, we have some provisions for that, but we don't really have a provision for a crosswind or assessing a crosswind accelerations. Then towards the end of stage 3, RWI, who were doing the wind tunnel tests, completed sort of a test to inform our design. On this side, which is quite interesting, we've sort of seen a reduction of wind loads in the sort of south and west direction of like nearly 50%. If you're in London, you sort of know that, or design buildings in London, you probably know that the dominant wind direction is from the southwest, dominant winds. So that in turn enabled us to remove the sort of spine bolts in the stability system. And we sort of like only needed, after that exercise, a level of one level of outriggers at level 22. Going quickly through some of the sort of floor plates, they're kind of relatively sort of straightforward. Everything is organized around the core. We have like predominantly parameter columns, plus a couple of internal columns. And then doing kind of like a stage 4, or like a revisit of a stage 4. So if a native land felt they had to introduce a second staircase, because that's sort of what the markets probably would expect after recommendations of Grenfell, and we sort of then incorporate that quite late into the design of the floor plates. Then you can sort of see how the building and floor plates sort of stats back at sort of above levels 21 and above level 38, and the core sort of getting more compact when we don't need as many shear bolts or core bolts for lateral stability system. One aspect kind of we looked closely at was the sort of like the outrigger bolts, which were located between level 22 and 23. We sort of like, as you can see on the sort of isometric here, we don't really have backspans to sort of transfer forces through the core. So we have to engage the floor plates, and they sort of pick up vertical forces due to gravity, and in compression sort of and tension, sort of as illustrated on the sketch. And then with respect to lateral loads, sort of pick up sort of reversal forces, compression and tension. So when we had to sort of design sort of the floor plates to sort of transfer the sort of in-plane forces in addition to the sort of flexural forces within the floor slab. This is sort of like an image how the kind of reinforcement distribution sort of looks like in the outrigger. As you can see, it's sort of quietly, densely kind of reinforced. Also, so you can see here the sort of reinforcement in comparison of an outrigger slab on the left-hand side, and the sort of more lightly reinforced post-tension slab of a typical slab. So there's a fair amount of reinforcement required to resist these sort of push-pull forces and these in-plane forces in the wall, in the slabs. So we also sort of decided to connect the outrigger to the overall stability system sort of like at a later stage. So we sort of made, and we left sort of a leave out effectively, so that the outrigger doesn't pick up the vertical forces on the upper floors. The connection was made when the superstructure was at level 35. The main reason for that is that the sort of cladding has sort of caught up installation at that point, sort of being just below level 22. And if you would have sort of done it any later, it would have been quite difficult to retrieve sort of formwork and essentially do wet trades and pump concrete to level 22. One critical aspect of like tall buildings, obviously, in particular in concrete, are movements. On this project, sort of the critical movements we needed to assess are the lateral movements, which are predominantly a result of the sort of uneven distribution of gravity forces, because we have the change in building mass. So you can sort of see on the sketches on the floor plans that we have sort of sometimes no load on one side of a core, or less load, where the building sort of steps back. So that results in sort of in the long term at sort of lateral deflections, which we estimated to be in a region of about 30 to 40 millimeters. You can obviously correct that, sort of like as indicated on the diagrams during the construction stage. So it's just after construction, whilst you build the building, but after that, you have to sort of make a provision in your lift shaft sort of tolerances to be able to absorb that movements when they sort of realign the lift shafts and to sort of ensure plumbness. The other aspect of sort of dealing or having to deal with issues due to building steps is that you have uneven loading sort of between the columns which sort of carry loads. For example, at sort of level 21, and from a superstructure from 20 floors above, and then columns where the building steps out on the terraces, or where the terraces are, which have nearly no load. So that sort of creates sort of like some challenges with respect to controlling the differential sort of movement. We've assessed this using construction stage models in ETUBs with sort of material parameters modeling sort of reinforcement, sort of composite columns and various concrete strengths, and we sort of went for an optimization sort of like process to basically meet these design criteria for differential sort of shortening through the use of sort of for the optimization of the use of composite columns strengths and reinforcement ratios, which was quite a sort of laborious process. In addition, we also sort of like tested the modulus of elasticity after having conversation with London Concretes in terms of what they could achieve for a mix. We have like a mix called Dynamics for higher strength concrete, and you can see sort of like in the table compared to prescriptive sort of values of a Eurocode, when you achieve sort of increases in modulus and of elasticity of about sort of between 10 and sort of 20%, depending on the strength rate, which is quite a huge improvement. That sort of also enabled us, in combination with some value engineering, to remove most of composite columns above level 1. So the client sort of in that exercise accepted like a slight increase, which sort of reduced the cost quite significantly for the project. We obviously interested also in sort of like checking in terms of what we predicted and what we actually observe on site with respect to movement. So we receive regularly updates from Multiplex with regards to the verticality of the structure and the essentially sort of like have seen sort of like a sort of good agreement with our predictions. So we predicted at this stage that the sort of core would move laterally by about 5 millimeters, and on the right hand side you probably can't quite see it. Yeah, sort of in the ranges between 2 and 4 millimeters. in terms of plumbness of the core. So that's like a reasonably good agreement. We've done the same comparing the actual shortening. So we have received sort of monitoring data for up to level sort of 40 or completion up to level 40. There's still sort of like 9 floors on top of that. And at the lower levels, sort of like you can't not see it, but we sort of predicted values in a range of 10 millimeters for the actual shortening at level 10. That's sort of in good agreement. We sort of slightly at this stage sort of over predicted the sort of like shortening at level 20. Considering there's still some maybe 9 floors to come, we're probably in the right region within our prediction, which is sort of good news and giving some comfort what we sort of used in our analysis of values in terms of stiffness was sort of adequate. When you design the tall buildings with high strength columns, so you have to sort of then also deal with the issue of the joints between the columns and the slabs. There's some guidance from a Concrete Society and also in FIB Bulletin 101 how to deal with this. But once you sort of achieve higher or use higher strength or very high strength sort of concrete for the columns, so if you can't really sort of make use of the enhancement of the slab strength given in these sort of bulletins and in the concrete advice, does not really sort of achieve what you need to achieve in terms of strength. Similarly, if you would use sort of the enhancement due to confinement, if you would specify more links. So we decided to then specify that the slabs around the columns should be cast in a higher strength. And whoever sort of done this before know that you will not really sort of be loved for it by the concrete contractor, and they're kind of resisting it a little bit. And experience this way sort of get it wrong as well, and then cast the section in lower strength concrete, which may create issues later on. Keltbray sort of when we were bidding for a project sort of suggested to use precast column, which sort of gets around the issue, and then using essentially butt joints where the sort of column projects to the top of the slab. That solves some of the issue. It sort of raises, on the other hand, some sort of questions about the design of that butt joint. There's not really sort of like any good guidance given in the Eurocodes to how to deal with the issue. There's not really a satisfactory answer we sort of could find sort of anywhere else on sort of UK-based sort of guidance. However, sort of remember that I went to Germany and met was a university, and that was at a time when they built the sort of towers in Frankfurt, and they use precast columns. And if I would be sort of in Germany, I would sort of follow the guidance in sort of Heft 499 or some sort of documentation in the sort of Checking Engineers magazine. And in Germany, one would specify a steel plate at the end of the precast column or a steel mesh to sort of prevent sort of failure modes as sort of shown in the center sort of picture, upper center picture of the site, which is like spalling, and then sort of a reduction in sort of column cross section, and then essentially an ultimate failure. So that achieves sort of confinement of a reinforcement. You don't necessarily have to continue other than a continuity bar or tie bar for robustness through that interface. That wasn't liked by Keltbray, the contractor, and we sort of adopted then a more conventional solution by using grout sleeves and sort of traditional laps in the sort of reinforcement. And here sort of some images of the precast column, how that looks being made and sort of being installed and slide. The grout sleeves were put at the sort of top of the columns, precast columns, and then sort of flooded with grout, and then the kind of the precast column then the other one placed on top. we've done this for most of the columns. Some of them we didn't quite get to work, because with that you get like reduction in internal lever arm, which is sort of critical where you have sort of slabs and sort of large moments. And we use sort of traditional Payco system, sort of as shown here, and so that's being placed on site. And that's sort of almost the end of my presentation. I'll just sort of show a few images of the sort of basement construction on the left at level 4, at sort of like level B4, housing the car stacker, sort of around building 1, which is sort of still sort of an open to the air and to the elements, and some illustrations of the sort of the base of building, where we have the colonnade, so spanning our columns, 4 floors being constructed, and some images of the sort of PT slabs and the frame, kind of like at the early stages. That's thank you. That's the end of my presentation. I would also like to acknowledge sort of the team working on this, with Maria, Alex, and Miguel, who have sort of led our design team from the early stages, concept stages, to delivery of the building. We're almost done. I think it's sort of building tops out in sort of a month or so, and hopefully sort of will complete soon. With that, I hand over to my colleague Pavel, who will talk about the Nine Elms project.
Good evening, everyone. Thank you, Christian, for the introduction. So my name is Pavel Gryba. I'm working as a project director at AKT. What I'd like to present today is remarkable projects of Nine Elms. So just introduction to the projects. So we been working for client on the group with architects KPF, MEP engineer Sweco, basement contractor Kerry, superstructure constructor Byrne Brothers. So piling contractor was Balfour Beatty Ground Engineering, and main contractor Multiplex. Nine Elms is strategically located in northeastern tip of the London borough of Wandsworth, specifically of the ward of Queenstown, where the site is on the junction of Nine Elms and Wandsworth Road, at the heart of the wider Nine Elms regeneration area. Development is surrounded by key regeneration projects, including the new Covent Garden Market next to US Embassy Garden, and the redevelopment of a Battersea power station to the west. It also benefits from the extended Northern Line station. So site history. So Nine Elms was swampy flooded prawn zone of the Thames. Its name is believed is back to 1645, when the Roan of Elms tree line on the road through the area. A key historical infrastructure element is a large Victorian trunk sewer which ran east-west beneath of the site and is remain operational today. Prior to the current development, on site was occupied by the Market Towers, which is 23-story commercial building constructed in 1975, which was approximately of 88 meter tall. The building was demolished for new development, and we can see this one on in the bottom on the photo. Ground condition across the area and the site are very complex, featuring 2 distinct soil profiles. In the western portion of the site, we have a typical London stratigraphy, including made ground, alluvium, terrace gravel, London clay, Lambert group, and tanned sand. In contrast to the eastern portion of the site, contains an ice age scour feature that disturb the layering profile, resulting in highly variable ground condition. This variability demand imposed challenges on the foundation solution, and what was proposed on the project, it was deep rotary pile, 60 meter below the raft. Site is very close to the river, therefore was proposed to use diaphragm to manage the water and create a good seal on the perimeter. One of the major site constraint was existing Thameses Water Victorian sewer, which is 1.7 meters diameter and is running diagonally across the site, just below the proposed B1 level. And shallow depth and operational status, that means that diversion on the very beginning, what was proposed on the development, was very expensive, and it was discounted on the as an option. As a result of this one, that imposed create a lot of challenges, and as one of the tower is support, or the columns are lying just on top of the sewer, and we had to create transfer structure to bridge it. So what the project is about? So we are having two tower. River Tower, which is 40-story structure, which is hotel and residential use, approximately of 160 meter tall. Second tower, which is 57-story structure, which is residential use with a plant area on the way. Below around the river tower area, we have a podium, which is a hotel reception and residential terraces. City Tower. So the height of the tower, it is 208 meters. Is the taller of the two buildings, is a purely residential. Structural stability system is reinforced concrete flank with the buttress wall, and in the middle what we can see how the buttress wall are step back along the height, so not all of the walls are going to the top, as the massing of the building is stepping out. The floor system are post tension with a maximum span around 7.2 meter, designed to optimize the floor to ceiling zone. The towers employ a combination of the composite reinforced column and RC column to reduce the area of the structure and maximize the net area. Slenderness ratio of the tower is 6, and the sway target is limits age over 500 to ensure both comfort and especially in the wind condition. River Tower is approximately 160 meters, incorporates of both hotel and residential use. Unlike City Tower, it rely on just central core for lateral stability. The structural floor are post-tension concrete with the spans up to 9 meters, allowing flexible internal layout. Composite columns are used up to level 14 to optimize the space and the performance, especially in the hotel area. With a slightly lower slenderness ratio of 5, the same sway control limits were developed were used in design, which is AOH over 500. Design can be very complex, and this is one of the feature what we had to do in order to design the structure. And We had to test materials. We had to look at the tolerance during construction, movements, control the deflection and the sway so that facade can accommodate this one. We had to design the slabs and other elements like composite columns. On the very beginning, we had the composite columns going all the way up to the structure. However, through the various of the VE exercise, we had to reduce them. And in the superstructure, rather than composite columns, we adopt the high strength concrete, which Christian mentioned in his presentation, is imposing some challenges where we have a junction with PT slabs where there is a different grade of the concrete and the PT slab. Stability elements. So CT tower, it is rely on the core and outrigger solution, where the river tower it is rely on the core only. On the very beginning of a stage 2, we did quite a lot of study to address and optimize the core layout. We've been through the various of the options. So the CT tower and the bottom core wall thickness are 750, and they are reducing or stepping back through the height of the tower up to 300 millimeter. River tower, the core wall thickness are starting with a 500 at the ground floor level, and they are reducing up to 300 in the top part of the building. To improve lateral stiffness of the building, we had to look at steel section embedded in the spandrels. The main reason for this one was in the residential area where the floor to ceiling height is a very, very small number. The spandrels are quite shallow, and we struggle on the very beginning to make it to work. However, when RWDI provided wind tunnel results for this one, and lateral forces reduced, that will allow us to optimize this further. And in the end of the day, we pretty much VE most of the elements. We've used only in the bottom portion of the tower. Composite columns, where we did on the very beginning of the project, we did a variation and optimization of the columns. We've looked at the area, and in the river tower, the composite columns are proposed up to level 16 to optimize the area, especially in the hotel area. City tower, again, it was a quite high pressure to gaining as much area as we could. That's why the composite columns were introduced up to level 38. With changes between the standard column C50-60 to composite columns, we've reduced area of the columns by 50%. Axial shortening and the presetting strategy. It is quite unusual behavior of the tower when we are having composite columns. So generally, on the right hand side in the bottom picture, what we are seeing, that the shortening of the columns generally is bigger than the core. Because we had the composite columns, this behavior is reverse, meaning that the shortening of the core is bigger than the column. So that is imposing certain constraint on design and how the core is going to get constructed. Considering behavior of the foundation, shrinkage, creep, and elastic shortening of this one, the decision was made to preset the core. Core was preset from ground floor up to, let's say, 2/3 of the height of each of the tower. The presetting value was starting from 10 millimeters, and the maximum presetting which was used, it was 45 millimeter. Substructure. Because two towers are sitting on one of the basement, the that creates some challenges on the foundation solution. So what we had a double story basement. 2 towers were founded on the pile raft. City tower was founded on 3.5 meter raft, and river tower on 2.5. We are going to show more details shortly on this one. And as a retaining solution, diaphragm was proposed on the perimeter of the building with a variation of the depth to get seal and interlock within the clay. As I mentioned at the very beginning, it is quite highly variable clay layer on site due to the scour feature, and the difference in terms of the height between of the panel and the clay. Sometimes it is up to 7 meters on site. So what we are seeing, this one is a forest of the pile on the left hand side. This is the main reason, because the existing structure or existing building, which is 23 story market towers, were founded on 900 shallow foundation, shallow pile foundation, and these piles were pretty much core through to allowing for new development. We could not use existing piles because from the excavation it was just 6 meters of the piling what's left over without any reinforcements. So we had to put a large diameter pile going to the tunnel, and in the river tower area, the pile diameter are from 1500 to 2.1 meter. All of them are rotary board. The city tower is from 1500 to 2.1 meter. In the podium area, it was 900 to 1800, and in the other area are 900 to 1500. Because of the top-down methodology, we had to increase certain pile diameter for allowing for the plunge column installation. On the right-hand side, what we are having is the average thickness of the raft, and in the river tower, it is 3.5 meter. In the river tower is 3 meters, city tower it is 3.5, podium is 1.5 and the other remaining area of the basement it was 750 millimeter. Because of the complex ground condition, we had to do solid structure interaction, and we did this one with the 3 different software packages. So the ground model was done in the Plaxis. We developed this one. We sent the spring stiffness and the solid stiffness into Sophistic with the loads from construction sequence from ETABS. So superstructure, both towers were modeled in ETABS. The raft and the basement was calculated in Sophistic. Construction sequence. To speed up construction sequence and Multiplex proposed top-down construction methodology. Because it took us nearly 3 years to construct the pile, it was high pressure to build superstructure as quickly as possible. That means that we had to design the ring beam to support the core, and plunge column were installed in the piles. That allows us to progress with the superstructure at the same time, dig the basement and construct the raft later on. And what we are seeing over here is a part of the ring beam design which we did in Sophistic, because there is a very little, let's say, knowledge or guidance in Eurocode how to design this elements. We've used one of the research for the Smart Coco project, where they did tests how the plunge column are behaving within the and within the walls with the shear studs. Next one, I have a photograph from side. So on the right hand side is a ring beam with reinforcement and plunge column sticking out, and on the left hand side is a photo from inside of the basement. Because of the volume of the raft, river tower and city tower the raft was poured continuously. So that's mean that it was 4,852 cube meter of concrete poured in once. It took pretty much 30 hours to pour this one, to pour the raft, and it was 642 wagons of a concrete. So that was quite heavy traffic, and it was continuous pour. So that was quite interesting experience for the contractors, subcontractors, as us, as well as we've been present on site. On the right hand side, what we are having is a picture of the top-down construction methodology. We are kind of seeing that the core and the slabs are flying through, where the core wall in the basement has not been constructed yet, and has not been constructed yet, and the hold point. So to what time they had to finish core, Multiplex advised that at the time that it can be constructed 16 levels of the core in the river tower and 21 levels on the city tower. Through the concrete placement, we found some issues in the ring beam elements. It was quite dense over reinforcement, and what we found it is issues with the concrete placements. Honeycomb was observed, and not everywhere we've seen we had the concrete. As a result of this one, so it was investigation or investigation required. What has happened? We took quite a lot of core sample, was taken through the core, and independent expert from the concrete center service was brought as well on the journey with a methodology how to repair this one. In the end of the day, the defects was repaired, and a lot of sample was taken. And even on the right hand side, what we are seeing, this one is a core through the core with some voidage, let's say, present. Through the concrete strength results, we've seen that is still, even with this voidage, the concrete strength was achieved. The specification what is required. Some of the interesting stuff. One of the Saturday work through the demolition of the infills in the ring beam, the demolition contractor cut permanently through the permanent spandrel. That's imposed a lot of kind of challenges from our end, how to reinstate this one in the permanent condition, especially if we had steel sections and quite a lot of reinforcement. So it was heavy welding on site. And I just would like to show, let's say, a few photographs from the hotel, because the hotel is operational now. It took us pretty much 10 years to design and construct on site, and some of the view from apartment. So towards the end of the journey of the design, after building was pretty much complete, what we did with the design team, we tried to climb up from B3 to level 57, and it took us 21 minutes. So the record, it is still, I believe, for Multiplex, because one of the guy climbed up in less than 7 minutes. So thank you very much for time.